Welcome to 9.5, light energy. So we've just looked at the electromagnetic spectrum. Well, let's look at the specifics of light energy. So light travels through space at the speed of about 300,000 kilometers per second. It makes life on Earth possible in regards to things like photosynthesis, and it allows the animals on Earth to have eyes and see the fantastic things around us. What we're looking at here is a lighthouse in a fog. So the fog, scatters the light as it tries to head out. If the fog wasn't there, you would just be seeing the lighthouse itself. But as the fog kind of scatters the light in all directions, you get this nice haze of almost makes it look black and white, I suppose. And it's all kind of, the light is scattered all over the place. But usually light exists as a beam, which we'll see in a second. So this idea that light is projected in all directions is absolutely true, just because it really exists as a collection of beams that fly out from a light source. So even from here, the light's really flying out as a collection of beams. And as we'll discuss later, whether it exists as a wave or as a particle, I suppose, was under some discussion. And in fact, actually, let's do that now, I think. The particle model was really discussed by Isaac Newton. He looked at the refraction and reflection of light, which we'll have a look at in a moment, and how he calculated the angles and said, well, the way it works when it hits and absorbed by stuff, that really basically says that it has to be a particle. So there's particles that are flying out from a light source and then bounce off, in very predictable ways, much like a ball being thrown against a wall. It's very predictable if you know the right mathematics, exactly how that ball will fly off, and so it is with light. So Isaac Newton projected that it was that light must be a particle. However, there is good thoughts at the time that it actually existed as a wave. Now, there was a man named Thomas Young. He basically said at the time that, well, that's all very well and good, but the light, as it travels through a medium, it doesn't really travel much like a particle. It can travel through mediums such as water and through glass and whatever else like that. And in that way, it really acts very, very much like a wave. It tends to go through things. It doesn't tend to bounce off things like water, like you'd expect a ball to, or particle to, or it doesn't really, it's not stopped by glass, which you'd expect a lot of particles to be stopped by. So there was some discussion on that. It wasn't until we started to get to Einstein that we started to understand a bit more of the quantum mechanics and understand that in certain situations it does exist like a wave, as it travels through particles, but it also exists as much like a particle. Photon is what they ended up calling this particle when it's absorbed and reflected. So it's a bit complicated because it does kind of exist in both ways, I suppose. Everybody's right in their own kind of a way, and I suppose everybody's wrong in their own other way. So let's have a look at how light works as it moves through objects. Okay, so we're going to move through this as quickly as possible because it's not terribly complicated. So there are different types of substances that the light can go through, which is completely transparent, translucent, and opaque. Transparent substances that go straight through, translucent substances that can get through, but not all of it, and and opaque substances that are bounces straight off of or is absorbed. All right. There are substances that it is reflected from that are curved. And what this does is the curves cause the light, when it hits here, to bounce off in odd kind of directions. So you don't get a flat image coming back to your eye, you get all kind of weird stretched images coming back, because the particle that you would expect to kind of come back straight back actually ends up bouncing up this way, so you kind of see the stretching of his face and eyes and all this kind of stuff. The last image here is of an ambulance, and the reason why we've got a picture of the ambulance here is because of this sign here. They've decided to put it on backwards, because when you're looking at it in your rear view mirror, it appears in exactly how it should. Let me explain that in a bit more detail. So the light of this A bounces off this way, all right, and hits your rear view mirror. So that means this A appears here, all right? And then the light from this one, the M, bounces off, and then you see the M. And the light from the B, U-L-A-N-C-E, ambulance. So you can imagine, if this is on the right-hand side, okay, but you're in front of this car, looking at it in your rear view mirror, it would still, sorry, it's on the left-hand side. Yeah, it's on the left-hand side, and it still appears on the left-hand side. Yeah, so this is A and then B, M and then B, U, L, A, N, C, E. Well, I'll explain this a bit more in class because it might be easier to do with an actual mirror. But hopefully you get the idea. Lastly, odd little light effects is light as it travels through water. Now, light travels at a different speed through air as it does through water. So that means it slows down. And as it slows down, that means the angle of refraction changes. So what you end up getting is that the toe looks like it's here, but actually the toe is here. So the body should extend down. It actually is here. So what you end up with is these pictures where it looks like he's got these little stumpy legs and weird kind of malformed arms, where it's just because the light is kind of hitting this point and then is coming down at a much sharper angle than it otherwise would. Yeah, so the light is coming down here and it's hitting down much sharper than it otherwise would. All right, and that means that it doesn't look like it where it is. And it's actually a big issue for hunters. You tend to find people like those Aboriginal tribes in the Northern Territory who have adapted very, very well to being able to take a spear and stab fish in this, in a body of water. Now they know that where the fish is not where you should, throw the spear. You've got to throw it, a certain distance away from where you think it is. And that seems unintuitive for a while, especially for someone like me that has no idea about any of that kind of stuff. But for them, it's very intuitive as to where they should be throwing the spear, knowing that where they see the fish is not where the fish actually is, which I find fascinating. So let's have a look at some ray diagrams. Ray diagrams basically talk about, if you had a light ray, I suppose, coming out from your nose, these are where, those light rays would be occurring, where they'll be bouncing. Now, when you're looking at a mirror, you can actually, the image you're seeing appears at the same distance as an angle of refraction, in the image. So this is all an image. So if you did an imaginary line, this would be the angle of refraction, and that's where the nose would appear. Where that part of the nose would appear. But the angle of reflection is just out this way. Similarly, if we look at concave versus convex, concave, you should always, it's easy to remember the difference. Concave looks like a cave, and convex does not look like a cave. So with concave mirrors, the light comes in and is bounced towards a single point. Okay, and this is called the focal point. The focal point is where all the rays intersect. All right. However, with a convex mirror, all the rays kind of bounce outwards, and the focal point is almost like an imaginary focal point, calculated as where they would meet. And it's this focal point that, for example, the eye would want this focal point to be at a particular point inside the eye, in the retina, so that you can see things. All right, so that's it for chapter 9.5. What I'd like you to do is to copy the blue words into Quizlet and then answer questions 1 to 8, and I will see you in class.